Hi, welcome to StatStuff. I'm Matt Hansen. This lesson is part of an extended series on hypothesis testing in the analyze phase. In this lesson, I'll review the Mann-Whitney test, which is a non-parametric test used when comparing the central tendency of a continuous value to itself across different time periods, locations, or groups. I'll spend the first part of this lesson reviewing some of the critical concepts that can help you to understand how to use this test. But despite that, I recommend that you at least review the prior lessons on hypothesis testing if you haven't already done so. But for now, let's start with reviewing again why we even need hypothesis testing.
Well, we need hypothesis testing because, remember, our goal for the project is to resolve the problem by first building a transfer function. We don't want to just alleviate the symptoms that we're seeing, but we want to get to the root cause. You may recall my example of my daughter Hannah. We don't want to just alleviate the arthritis pain that she was feeling in her leg, but we want to heal the root cause, which was the strep throat. So if we don't know what the root cause is, then that means we need to build a transfer function to figure that out. By building the transfer function, we can know what changes, that is, what improvements that we need to make that should fix that root cause. Now, if you recall, the transfer function is defined as y equals f of x. That is, the output response of y is a function of one or more input x's. It's part of the IPO flow model, again, that we described before in the IPO flow model, where we have an input that leads to a process and an output. Well, the y refers to that output. The process piece refers to the function that's applied to an x, the x being the inputs that are part of it. So it's really expressed in the IPO flow model to an equation. Now, how does this transfer function fit with hypothesis testing? Well, hypothesis testing tells us which of those x's, which of those inputs that we're looking at, are independently influencing the y, the output metric. When we reject a null hypothesis, we're building evidence proving which x's are guilty of driving the y. And what we'll do at the end is we'll compile all the evidence in the improve phase of DMAIC, and that's when we'll begin to fix those root causes or come up with a plan that's going to fix those root causes. Now that we know from the hypothesis testing which of the x's are the most critical x's that have the most influence and where we need to make the biggest changes that are going to affect our output y.
Okay, now let's review again the various steps that we follow when doing hypothesis testing.
At a high level, the steps begin with a four-step process, which was starting with a practical problem. We're stating the problem as a yes or no question, and then we want to convert that problem into a statistical problem. That's going to help us to figure out which is the right statistical tool or method we're going to use to help figure out how we're going to do the analysis. And then we apply that statistical tool or concept on it, and then we interpret the results from that and come up with some analytical answer. And then from that, we would interpret the analytical answer into some practical solution or some practical way in applying that so it would make sense to us. And at the heart of doing the hypothesis testing, again, for steps 2 or 3, that's where we drill down to 6 additional sub-processes or sub-steps in order to figure that out. So it started off with defining the objective. Then we want to state the null and the alternative hypotheses. Then we define the confidence level and the power levels based off of the alpha and beta risks that were identified. Collect the sample data, and we want to calculate the p-value. All these are part of building this statistical problem. And then once we've done that and run the test, then we interpret the results. This is going to be the point where we decide whether we're going to accept or reject the null hypothesis. This is what we'd follow when we want to go through the formal hypothesis testing.
All right, now let's review again the chart for finding the right statistical test and where the Mann-Whitney test fits into all that.
We'll refer again to the drill down where we find the right statistical test. In this case, we're talking about a continuous value where we're going to be looking for central tendency for that. And in this case, we're going to be drilling down the path where we're assuming that the data is non-normal. When the data is non-normal and we're comparing two populations with each other or two different groups, then we're going to be referring to the Mann-Whitney test that we're going to be covering in this particular lesson.
Now let's review again the concept of confidence intervals, which is essential for understanding statistical tests like these.
We have to remember the confidence intervals are an estimated upper and lower range of the mean. So the confidence interval will change or become more narrow when you add more samples. So example we've given before is when we have fewer samples, the population mean falls somewhere within this wide interval. But as we get more samples and distribution grows, the confidence interval represented by these dashed lines gets more narrow. So as we get more and more data that increases, then the confidence interval gets more and more narrow because we could be more confident having more data where the population mean should fall. So we've got to remember that statistics are intended to help us make inferences about a population. So let's say we have a mean of 57 with a 95% confidence interval that falls from 55 to 59. Well, that would imply that although the sample mean is only 57, then we can have 95% confidence the population mean will fall somewhere between 55 and 59. So the more data that we collect, the more narrow this interval becomes. So if we were to double our sample size or triple our sample size, then the confidence interval might narrow. Again, we might come up with the same mean of 57, but it might make it more narrow, where now the range is between 56 and 58. So it gets more and more narrow with the more data that we collect. So the first step that we have in hypothesis testing is to define the objective by asking, is there a difference between something, or whatever it is that we're comparing? Now, the statistical test generally will compare the different confidence intervals between factors to see if that difference actually exists. So an example we've given before is, let's say we only have 20 samples we pulled and we're looking at the difference between factor A and factor B. We might have a mean here at this value for factor A and a mean represented by the dot here for factor B. And the line spread out across each one here between each factor represents the confidence interval. So for factor A, the average actually falls just above 3, maybe like a 3.05 or something like that. And the confidence interval here shows that the population mean actually could fall as low as maybe 2.7, or it could be as high as, in this case, maybe like a 3.3, somewhere within this range, even though the dot represents this is where the mean falls. Well, for factor B, this mean falls at this dot, and that means the population mean can fall somewhere within this range. So you got to remember the tests look for the overlap between the confidence intervals. If there's a lot of overlap between them, then there's a good chance that the actual population mean between the compared factors are possibly the same, or very close to being the same, which is going to result in a higher p-value, a higher level of risk before we can claim any difference. Well, the more samples we collect, then there's going to be more narrow confidence intervals. Having more narrow confidence intervals means there's less of an overlap between them. So that means there's a lot less chance that the population mean is going to fall within the same more narrow spot between both of these compared factors. And as you continue to collect even more data, then as shown here, there's no overlap. And if that becomes the case, then we would say that there's a low or no p-value where we can conclude, yes, there is a statistical difference between these factors after all.
Okay, now let's see how you can run the Mann-Whitney test in Minitab.
Well, for this type of test, we're going to use this when we want to compare the median values from two random samples across two different populations that have similar shape and variation. So think of that in terms of if you have some continuous measurement for comparing across two different groups, such as between two different people, two different teams, two different locations like a call center, or two different operation centers, or two different production lines, or maybe across two different states or two different countries or provinces, or whatever you want to say. If there's two groups that you want to compare against each other, you want to compare the median values, this is where this type of test would really fit in. This type of test is also referred to as the two-sample rank test, or the two-sample Wilcoxon rank sum test. So how are you going to find this within Minitab? Well, you go to Stat, Non-Parametrics, and then choose Mann-Whitney. And this is the kind of input that you'll see for the dialog box that appears from within Minitab. And in here, you're going to first select the columns that are going to contain the continuous data they're going to be testing. So you're going to have them set up across two different columns, and you're comparing them one-to-one. And you're also going to select in there the desired confidence interval for the median, and you also want to define how the test is going to be compared with the median values for identifying your alternative hypothesis.
All right, now let's go through an example of the Mann-Whitney test.
In this example, we're going to be using metric C for our sample values for the test. So as a background, we're going to go use that metric C column that's a part of the Minitab sample data file that's provided on the website. Now, we need to set this up in one way. As I illustrated before, the Mann-Whitney test is expecting the values to be in one column for one group and another column for the second group that you're comparing. However, metric C is all within one column. So what you need to do is copy the values for half of what's in metric C in that particular column and split it across two new columns, or just take half of it and put it into a second column. Either way, you want to be able to split up the data. There's 100 records that are in there. Split it 50-50 so that half of it is represented in one column, the other half represented in the second column. In this example, what we're going to do is label the first one as metric C1, and then the other remaining 50 represented in the other column as metric C2. So setting up the data like that, the practical problem we have for this situation is we're asking ourselves, is the median for metric C1 equal to the median of metric C2? So for the statistical problem, we're going to define it in this way. We're going to state the null and alternative hypotheses, where the null hypothesis says that the median value for group 1 is equal to the median value of group 2, and the alternative is that they're not equal to each other. Now for the confidence and power levels, we're going to use the default of 5% risk for alpha, and which is going to be our 95% confidence, and we're going to use 10% as our beta risk, which gives us a 90% power level. So the statistical problem of how we're going to plug in the mini-tab, we're going to go to the Stat menu, select Non-Parametrics, and choose the Mann-Whitney test. And the first sample box that you have in there in that dialog box, you're going to select metric C1, that first column from the list of columns. And then for the other one that says second sample, you're going to select metric C2, the second column that you had created. Now we're going to make sure that in the confidence level portion we're going to identify 95, and for the alternative portion select not equal, again because that's what we identified up here for the alternative. Our alternative is that it's going to be not equal to each other. So the statistical solution that we have as an output is going to look like this in the session window from within Mini-tab. So the p-value that we're going to be looking for, like we typically look for in most tests, is actually referred to as the test is significant at, and then whatever that value is, that is essentially what our p-value is. In this case, this p-value, since it's showing at 30%, that's greater than our alpha risk of 0.05, so in that case, we're going to fail to reject the null hypothesis. In other words, we're saying that we're going to accept the null hypothesis. We're going to believe that the values that we're comparing are about equal to each other. So from a practical standpoint, we're saying the sample that we're using in this data set is insufficient to prove that the median for metric C1, whatever is in that column, is different than the median of metric C2.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
I'd like you to refer back to the factors that you identified before for the output y and input x's that you're going to be comparing for doing all this hypothesis testing. Now for any factor that is a continuous value, I want you to try to use this Mann-Whitney test. Now again, in order to do that, you're going to need to compare at least two different sets of the same factor, like if it's across multiple periods of time or different locations or other types of groups that we talked about before, different locations, operations centers or teams or across states or countries, that kind of thing. Now, as a non-parametric test like this, it's going to be ideal for using non-normal distributions, but again, you don't have to, so it's okay if it's going to be run on a normal distribution as long as it's for a continuous value. You could also use other factors in your organization if you want to run it through this type of exercise as well. Now, before you run the Mann-Whitney test, again, ask yourself, do you expect that the medians of the factors that you're comparing appear to be different between them? And then run the Mann-Whitney test, and then ask yourself, are the medians of the factors actually statistically different from each other? Now, if the answers to those previous two questions are different, then ask yourself, how does that affect how you typically measure and communicate that factor from within your organization? For example, do the differences between the compared factors actually affect some financial decisions or maybe some process changes or other types of critical actions within your organization? If they do, then how should those results from the Mann-Whitney test be used in order to influence your organization? That is, should they change how the factors are normally compared between those different groups that you're comparing? Or should it change how that factor is measured? Or should it change how they react when they compare that metric in this way?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.